Hello there. In this video we're going to discuss briefly the concepts of two things that aren't usually introduced until about complex analysis, and those are called branch points and also branches. And we're going to discuss a topic that is connected to these two called multifunctions. So we'll be discussing multifunctions and how branch points and branches sort of connect with this new idea. Alright, so to begin this discussion of multifunctions, branch points, and branches, I'm just going to introduce a function that I guarantee you're probably already familiar with at that stage. And that's the function f of x is equal to x squared, where we're assuming that the domain of this function is the set of real numbers. And of course we know that the range of this particular function is the interval 0 to infinity. You also probably know the graph of this function. It should be a upwards facing u, assuming that we're taking the horizontal axis as x, and this is y, and of course we're defining this graph as f. So a couple of things about this function that we already know is that f is not one-to-one. That is, it does not pass the horizontal line test. So if the function is not one-to-one, then we know that f does not have an inverse function, right? Now, even though this curve f of x does not have an inverse function, it does have an inverse image, right? So if we reverse x and y, so if we define y to be equal to x squared, which is a relation, assuming we're allowing x to be in R, then this relation has this particular graph. So if we reverse the roles of x and y, and we have x is equal to y squared, then of course that is a relation in the xy plane. And let's assume this is x and y, then the graph of the inverse image of y is equal to x squared is of course a parabola on the positive x-axis instead of the positive y-axis. So of course this is a function, so that's no big deal, but it's not one-to-one, right? Now this other function is, or this other curve is not a function, but it is one-to-one, right? And this is a common property that you'll always find in between inverse images, right? Because the domain and range always switch between one another. Alright, so let's investigate this x equals y squared a little bit more. So I'm going to call this relation R. So I'm going to define R to be equal to the set of points xy such that x is equal to y squared, and we're going to assume that x and y can take positive real values, right? So of course the graph of that relation is this parabolic curve. Alright, so if I define a function in the normal way, and I say, okay, when I put, so the input of this, let's define it in this way. So if I say r of 4, well, what does this usually mean in terms of functional notation, right? So usually, if we have like, f of x is equal to x squared, then we say that, okay, f of 2 is going to be equal to 2 squared, which is equal to 4. All right, so if r is the inverse relation, whatever that means, then f of 4 should be equal to 2, right, by this logic. But we also know that f of minus 2 is going to be equal to minus 2 squared, which is equal to 4 as well. So you can also say that this is equal to minus 2. That's also fair. So in a way, this relation sends the interval 0 to infinity to pretty much the entire real line, right? But it does not do it in a unique fashion, right? Because it sends it to r plus and r negative. It sends one particular x value to two different y values. So this is what we're going to call a multifunction, right? So it's a multifunction, right? And for this particular example, it's very easy to define it, right? So we can define r, which sends 0 to infinity to r in the way such that r of x is going to be equal to plus or minus the square root of x, right? So it's going to be both of the roots of that particular number, right? So let's look at that particular graph again in a more detail, right? So we have this piece right here. So this piece right here is y is equal to the square root of x. And we have this piece right here. This is y is equal to negative square root of x. And we have the point for which these two pieces sort of meet together. So usually people do not like multifunctions because usually you like a unique output for a particular input. So what we can do is we can split this multifunction up into two pieces. So we can define, say, r1 of x to be equal to the square root of x, and r2 of x to be equal to negative square root of x. So now we have two relations, which are both functions, and they're both one-to-one, right? And remember that this is the inverse of f of x is equal to x squared for x greater than or equal to 0. And this is the inverse for f of x is equal to x squared for negative x, right? And of course, for these two relations, we can set x to be in the interval 0 to infinity, or r plus. All right, so these two functions have particular names. And this is where the idea of branch cuts and branch points begin with each other. So the pretty much idea is, okay, I have this curve, y is equal to x squared. It has an inverse image, and it does have some particular applications to me, but I would like a unique value output. I have this top piece and this bottom piece. Most of the time we like things that are positive, and usually we like things that cover pretty much the global behavior of the entire function. So two main things that we like: positivity, sometimes including the origin is okay, and covering the vast majority of the behavior of the function. Right? So we have two what we call branches. So I can call the top one, say, branch 1, and I can call the bottom branch 2. And the point for which these branches sort of meet together is what we call a branch point. So these branches sort of partition the multifunction into sub-pieces that are single-valued functions or just functions. So there's a thing called a principal branch, which is what some people can call the best branch. So principal branch can sometimes be used synonymously as the best branch of the multifunction, right? So typically the principal branch of the inverse image of x squared is typically this symbol y is equal to the square root of x, right? This symbol denotes the principal branch of the multi-valued inverse image of x squared, right? So when we say y is equal to the square root of 4, as we should know already that this is equal to 2 and only 2, right? This is not equal to minus 2. And why is that? Well, this symbol coordinates to the principal branch. So this is the principal branch of the inverse image of f of x is equal to x squared on the entire real line, right? So the inverse image of f of x equals x squared, so f of x is equal to x squared is this curve, its inverse image is this, and we take the principal branch to be this top piece. So by definition, this top half is the principal branch, and we denote this by f of x is equal to the square root of x. So by denotion and convention, we take this symbol square root, this little radical symbol, as the principal branch of the inverse image of f of x equals x squared on R, right? So that is pretty much a basic idea of branches and branch points. And of course the branch point here is 0, 0, because we can connect another branch I guess you could call it the secondary branch, since there's only two of them, that sort of encapsulate the rest of the behavior, right? So the second branch of f of x equals x squared will be negative square root of x, right? So we have two roots of 4, 2 and negative 2, right? But there's only one square root of 4, and that's the principal branch, which is 2, right? And of course, there's some discrepancy among the literature on this, but that's pretty much the idea of what we're trying to show here. All right, so there is some notation that is sometimes commonly used. So we have f of x is equal to x squared, where x belongs to R, and then we're talking about principal branches of inverses, right? Because its inverse image definitely is multi-valued. So we can define, so f inverse, we can call it, say, sub 1 of x. So this is going to be equal to the square root of x, and we can say f inverse negative 1 of x is equal to the negative square root of x. So we can say this is the principal branch, and we can call this the secondary branch, right? Principal branch is the, the one we call is best. Of course, it's subjective, right? Now, you can call this the principal branch, but in the current literature and what we've been using for several years, the principal branch of x squared's inverse image is just the positive square root of x. All right, so now let's look at another example that is not quite common. So let's consider the relation R that is collected by the points x, y, such that x cubed plus y squared is equal to 1, right? So maybe or maybe not, you know what the graph of this relation is, but you should at least have software to be able to get that. So it pretty much has this almost circular arc here, and then it has this in behavior that has this type of thing. So it crosses at 1, minus 1, 1, and let's assume this is the x-axis and y-axis. So this is the graph of relation R. Now, is this relation a function? No. Is this relation one-to-one? Yes, and you can verify that. So this relation is not a function, so it's a multifunction, as one can say. So if I say, okay, what is R of 0, right? So R of 0 goes to two values. It goes to 1, and it also goes to negative 1, right? So it's a multifunction. So is it possible that we can create functions, one the principal branch, one the secondary branch, or maybe a tertiary branch of this function, so we can have, some inverses that we can algebraically work with and so on. So you should be able to see that if we break this curve at this point and have a top half and a bottom half, then we get two curves that are both functions. They're also, of course, one-to-one. And also the union of these two relations will be the entire relation R, right? So we can consider two relations, this piece and this piece. So I can call this, say, R1, and I can also call this, say, R minus 1, right? Two different relations, right? So how do we define these things? So R1 is the set of all points, x, y, such that x cubed plus y squared is equal to 1, and y is greater than or equal to 0, and R2 similar, right? So it's a set of all x comma y such that x cubed plus y squared is equal to 1, and y less than or equal to 0. Right, so both of these are functions. So which one of these would we call our principal branch? We don't have to call any one the principal branch, but I probably would call this one the principal branch because it has all the positive output values. Right? So this is the principal branch of some other curve. So it's the principal branch of the inverse image of this curve, right? Right. So this would be the inverse of this curve that I'm drawing, which of course is now one-to-one, but it has a principal branch to its inverse. So we're taking this, once we invert it, to be the principal branch, right? But of course, this curve I've drawn here in orange is a function, so it doesn't need to be partitioned. So for our branches, we chose this point, 1, 0, to be our branch point. So remember, our branch point is where our two branches of our curve that used to be pieces of our multifunctions are sort of joined together, right? And we only need this piece. Now you can partition this curve into smaller pieces, right? So let's draw this relation again, right? So this is our relation R. So what you can do is you can have this piece, you can have this piece, you can have this piece, and you can also have that piece, right? Now, are each of these pieces one-to-one in functions? Yes. We have 3 branch points and we have 4 branches. Now, this is a little bit insufficient because when you unionize any two of these, for example, you can connect this one and that one. That has the same exact properties. Moreover, you can connect this blue and this green, right? So the dark blue and the green together are still functions in one-to-one, right? So you can unionize those and call that a branch, and you can unionize light blue and yellow, and that's a branch, right? Now the branch points are a little weird, right? I mean, we still have 3 branch points, but these pieces in these branches aren't even connected, right? So connectivity or continuity is an ideal property, right? So positive values, overall behavior, and continuity are usually ideals when you're trying to decide where to choose branch points in order to construct your branches. All right, so let's look at a couple more examples that are a little bit more in common, and you're definitely going to see this as you proceed through pre-calculus. So I'm going to draw this curve, which you may or may not have seen in the past, right? And it's going to be a little wave, right? So I'm going to choose this value as pi over 2. This is pi. This is 3 pi over 2. This is minus pi over 2. This is minus pi. This maximum minus 3 pi over 2. And let's assume this is symmetric and periodic with respect to 2 pi, right? So one obvious property of this relation for which I've drawn, it is not one-to-one. And I'm going to call this function s, right? So you may recognize this relation. So s is the relation, in case you don't know, is the set of all xy such that sine of x is equal to y. Right? And if you don't know what sine is, that's okay. I'm not going to get into that here. So what is the inverse image of s? So what does s inverse look like? So s inverse is going to be the set of all xy such that sine of y is equal to x. So what does the graph of that look like? So instead of riding along the x-axis, it's going to be riding along the y-axis. And you can fill in the details, but it's going to have this type of property. Now, how do you know exactly where everything is? So this is going to be minus 1, this is going to be 1. So this is going to be pi over 2. So pi over 2 should correspond to 1, and minus pi over 2 should correspond to negative 1, right? Because we've just switched the domain and range values. Now, S inverse, the inverse image of S, is a multifunction, right? Because if I say, okay, what is S inverse 0? Where we're assuming the input of this relation is the x values, the domain of S inverse. So, of course, S inverse is going to have a few, actually infinitely many. So it's going to go to 0. It's going to go to pi. It's going to go to minus pi. It's going to go to 2 pi minus 2 pi. And it's going to continue on forever, right? So we have infinitely many values. In particular, S inverse of 0 is going to be equal to k pi, where k is an integer. Right? So infinitely many values. But nonetheless, S inverse is a multifunction. So is it possible to construct branches of this curve? In order for this curve, this new curve that we're building, to be a function. So remember, we want the overall property of this curve. Now, if I were to choose this top u piece, right? Notice if we choose that, it's not a function, so that's not going to work, right? And, the same can be said about this bottom half here. So if you sort of think about it, one of the most obvious branches one can choose is we can take the minimum, the maximum of its inverse, and connect the two. So we have this middle curve. Because this middle curve is going to repeat overall, right? So in terms of the y values for S inverse, we're going from minus pi over 2 to pi over 2, right? So I can define this, so I'm going to call this S inverse sub 0. So this is going to be the set of all x, y, such that sine of y is equal to x, and minus pi over 2 is less than or equal to y is less than or equal to pi over 2. So this is what I'm going to call my principal branch, right? Now, some people, I've seen several books, right? So the original relation r is sine of x, right? I shouldn't use the equal sign because one's a set and one's a function. So these two are sort of related. Now, what about this r inverse? Is there a notation for that? Now, you may see a few things. You may see this thing. You may see arc sine of x. You may see a sine of x. And you may also see capital ARC sine of x, or capital A sin x. Now, depending on the book you're using, one may be the principal branch and the other will not. But I'm not going to get into the battle of which one is which and which one I prefer, because that's a discussion for another day. Right? So, this curve, sine of x, is of course not 1 to 1, so we choose a principal branch of its inverse, so we can do like inverse trigonometric equations and stuff like that. So we have this piece and its bottom piece. So there we go. So this is going to be minus 1, 1. It's going to be pi over 2 minus pi over 2. So if I call this S and I call this S sub 0 inverse, so therefore the inverse image of 0 is going to be equal to 0, right? Instead of 0, pi, 2 pi, 3 pi, and so on, now we only have one function, right? Or one value, because this S inverse of 0, the principal branch, the branches should be single valued functions, right? To avoid the multifunction thing for which we were trying to avoid before. So if you're familiar with sine, then you should also be familiar with its relative. Some people call it cosine. So cosine is a wave that sort of starts up here and sort of does the same exact wave behavior. So I'm just going to call this relation C. Since we're not really talking about trig here, it doesn't really matter. So of course, this curve is not 1 to 1, so its inverse image is a multifunction. That should be obvious at this stage, right? And what does its inverse image look like? So instead of being on the positive y-axis with this little u, it's going to be on the positive y-axis for its inverse image, right? And then it's going to do its wavy pattern up the y-axis and down the y-axis, right? So it's going to have that type of wiggle behavior. It's a horrible graph, but hope you get my point. There we go. That's better, except the top half. Right. Horrible sketch. So this is my inverse image of C. Now take a moment to think, what should my principal branch for this function be, right? So my principal branch for this, I'm going to choose to be equal to, these are going to be my branch points, right? So I'm going to let this be my principal branch, right? So again, this is minus 1, 1, and this is going to be pi to 0, right? So C inverse, right? And some people will abbreviate this as like arc cosine or whatever. So this is going to be the set of points x, y, such that cosine of y is equal to x, and y belongs to the interval 0 to pi, right? So that's going to be my principal branch, which you can subscript that as 0 to denote the principal branch, or you can subscript it as pi. It depends really what you're trying to emphasize with this subscript. So that's going to be my principal branch of inverse cosine. So therefore, I can say, okay, what is the inverse image of the point 1? So according to this, when I choose x as 1 as my input value of x, I only have one value. In this case, it's going to be 0. So if I say, okay, what is my inverse image, principal branch, of 0? So in that case, 0 is going to go to this point here. So that's, of course, going to be pi over 2. And if I ask, okay, what is the inverse image principal branch of the point -1, then you should know that that's going to be equal to pi. Now, if I sort of go beyond this, right? So if I ask, okay, what about C inverse subscript 0 of 2? So what is the inverse image of 2, right? So that means the cosine of something is equal to 2. Well, this is not in the set of real numbers, right? So this is pretty much asking, okay, cosine of x is equal to 2, therefore x is equal to question mark. It's pretty much asking this type of question, right? Sort of like, when is the square root equal to a negative number? It's pretty much like that. So this is not in the set of real numbers because the cosine function, or this wave for which I've defined, is always bounded between -1 and 1, right? Therefore, this does not exist, at least in the set of reals. Now, what if you're not happy with this branch for which I've constructed? There's infinitely many branches, right? So why do I choose that one, and does that mean all the other branches are useless, right? So here's my entire inverse image, and here's the principal branch for which I claim is so useful, right? So this is my C inverse subscript 0. So what if you chose this branch here? In terms of the values, I mean, it's not too negative, not too positive. So and it's just the mirror image of C inverse 0, right? So this is a decent branch, right? It's definitely a branch. It's still a function. It's still one-to-one. It's still beautiful in its own way. And I guess I can call this like minus pi. So here I'm giving some meaning to these subscripts. So 0 here is going to be my bottom of this curve, sort of it traverses the curve upwards, and here my base point is minus pi, so it traverses upwards, right? So if I were to go to the next one, right, so the next branch will be this one, so I would probably call this C inverse 2 pi, right? So subscripting these branches with something meaningful, definitely a high recommendation. So if I define it in this way, and I ask things like such as, what is the inverse image with principal branch minus pi of the point 0? Well, that's still equal to 0, right? Because 1 comma 0 should be 1, right? No. So when you input 0 into this inverse image, that's going to go to -1, right? Now what is the inverse image of 1? So that's 0, right? Which is equal to C inverse subscript 0 of 1 as well. It's a branch point, and that's where those two branches meet. And if I say, okay, what is the inverse image under this branch of, let's do -1. So in this case, that's going to be equal to minus pi, right? So now we're looking at that point, which is the branch point of C inverse minus pi and C inverse minus 2 pi, right? Now, just defining branches and with the goal of making multi-valued multifunctions, functions with smaller pieces which unionize into the multifunctions, there's definitely other applications that are a little bit more useful. So let's consider the relation R, which is consistent of the points x, y, such that y is equal to x cubed minus x plus 1. So clearly I've isolated y, it's by itself, so this is a function of x, right? That's very easy to see. So this will pass the vertical line test, no big deal there. So I'm going to define this to be r. I'm going to define this as x, and this is y. Now does it have an inverse image? No, because this function is not one-to-one. But it's almost always one-to-one, maybe, right? And I'm going to use those words very lightly because they may mean something different to other people. So if I look in between these yellow lines, right, and one should be at least able to verify that if I ask you, okay, what is R of 1? So R of 1 is going to be equal to 1 minus 1 plus 1, which is going to be equal to 1. We can also have R of 0, that's going to be equal to 1. And we also have R of minus 1, and you can find out that that's going to be equal to 1 as well. So R of 1, R of 0, R of minus 1 all go to 1. And I guess this graph is slightly misleading because it's not supposed to necessarily touch there. So let me draw sort of what I mean. Okay, cool. This is a little bit better. All right, so we have 3 values, right? So we have R of 0, R of minus 1, and R of positive 1. Definitely not drawn to scale, but hopefully you get my point. So let that be 0, negative 1, let that be 1, and this is of course going to be equal to 0. So we have 3 values, right? There's some points for which I could choose that are 2 valued. There's some lines that are 1 valued, right? So if I choose points directly on this yellow line, that's going to be 2 values, there, and similar for the others. Now if I choose a point value greater than, say, y is equal to a, that's going to give me 1 value, 1 unique solution, and y is equal to b, that's going to give me another unique solution if I choose another y value underneath. So if I look at the inverse image, so our inverse of 1, this is going to be equal to minus 1, 0, and 1. Right? It's going to be equal to all of these. So clearly our inverse is a multifunction. Right? Now, what if I say, okay, what is our inverse of 7? And what is our inverse of minus 5? You can take a moment and see if you can figure out what these values should be. So if you take a moment, you should be able to verify that our inverse of 7 is going to be equal to 2, and our inverse of minus 5 is going to be equal to minus 2 only, right? And we're not talking about branches yet, right? We haven't chosen any principal or secondary branches. So if we have this type of curve, and I'm going to draw it slightly out of skew just to sort of illustrate. So where would you choose your branch points for this curve? So most of the time you want to change, especially if this is a function of x, choose branch points for your inverse image where the original has a maximum or minimum. So choosing branch points here and here are definitely guaranteed because that's pretty much forcing this non-one-to-oneness for this function, right? So if I were to sort of graph this relation, so this is relation R, what would the graph of its inverse relation be? So it's going to minus infinity to infinity there, it's going to positive infinity to infinity there. So maybe, let's call this something. Let's call this 0 comma alpha. That means alpha comma 0 is going to be a point on the curve. And let's call this point, say, beta comma 0. So that means 0 comma beta is going to be on the curve. So no. So this is 0 comma beta, and alpha comma 0 is going to be over here. And we have minus infinity and minus infinity over here, and positive infinity over there. Keep in mind these are not numbers, right? I'm just trying to get a sense of where my curves are. So we have some point over here, we have some point over here, and then we can extrapolate through these points, right? So this is going to be the graph of our inverse image. So if we look at where the maximums and minimums are going to be, which are going to be 0 comma beta and alpha comma 0, if we're just assuming those are what those points are, then I can define my principal branch in one of 2 places. You can probably choose this to be your principal branch, right? I can call this, say, R inverse sub 1, you could call it. You can call this branch R inverse sub 0, and you can call this branch here R inverse sub minus 1. Now why do I choose this convention? Well, clearly R inverse sub 0 has the least amount of points, right? It covers the least area. The arc length, at least, is the smallest. Now in terms of arc length of R1 and R negative 1, probably the same. You can verify that if you know some basic integral calculus. But I'm choosing this top one because it contains the most positive values. If you're interested in negative values more, you may define this bottom pink branch to be your principal branch, right? But notice I'm not calling any branch principal branches, I'm just notating them, defining them in such a way, right? And of course, our branch points, we have two of them. Those are 0 beta and alpha 0, which sort of join these branches together. Anyway, I hope that sort of gives you a basic idea of branch points and branch cuts for multifunctions. This definitely has a lot of applications once you hit complex analysis, and the definitions might shift a little bit because in complex variables you're working with sheets instead of silver curves because we're working in 4 dimensions instead of 2 dimensions. Definitely interesting things once you sort of get the hang of it. So I definitely suggest you check like Riemann surfaces out and things of that nature. Anyway, I hope this gives you a sort of idea of how to work with multifunctions and also how to work with inverse images of functions that are not one-to-one. Hope you enjoyed.